Hello and welcome to our video AP Chemistry Equilibrium, where we discuss LeChatelier's principle. Apologies to French teachers, French students, and the French. And even maybe people who know that I can't speak French. When a stress is applied to a system, the equilibrium will shift in the direction that will relieve the stress. K will remain the same. Okay, stress to the system does not mean changing temperature, changing K. It means we do something to product side, reactant side, the system itself, all sorts of things. And because equilibrium is always seeking K, whatever influence we've put on the system, our system will adapt to return the system back to equilibrium. So we can change concentration of reactants that are given in molarities. If we increase concentration of a reactant, equilibrium will shift to the right because all of a sudden you have an overabundance of reactants, which in your K equation would be the denominator, which would force our system to then try to increase the value in the numerator. Okay, now this is projecting reality onto a mathematical equation that human beings have built. The chemistry is the chemistry, though. The system is trying to return to its equilibrium at that temperature. A decrease in concentration of a product will cause the equilibrium to shift to the right and form more products. A decrease in the concentration of a reactant will cause the equilibrium to shift to the left to make more reactant. A change in concentration of a reactant or product will not affect K. K stays the same. What's important about equilibrium here is not that the phenomena of what happened, when you play around, it's that in industry and in life we can manipulate equilibrium to achieve a certain systemic content. If carbon monoxide is increased in this process, the forward reaction increases to reestablish the equilibrium. Therefore, quantity of hydrogen will decrease, in other words, it gets consumed, and the quantity of product will increase. The value for the equilibrium constant will stay the same. And you can test this out by messing with numbers and keeping your K the same value. These things are all experimentally determined, okay? But they're also mathematically provable. So this is just a graphic saying what's written in the question. K is K. Here's our equilibrium expression. And if this increases, then you're going to consume hydrogen in order to make more product. Okay? So we can think about, if we do this, what happens to all the species in the reaction? If a product is added to the system at equilibrium, the reverse reaction will increase and reestablish the equilibrium. Therefore, quantities of both reactants will increase. The value for equilibrium constant K is, again, unchanged. Questions abound of a variety in College Board world about how we can test your understanding of LeChatelier's principle in manipulating equilibrium systems. The question isn't just about, well, what's going to happen. It may be what happens to the pressure of partial pressure of hydrogen. It could be what happens to the pressure in the system. There are all sorts of ways to think about what could happen. Continuous removal of a product from a reaction forces more of it to be produced, according to LeChatelier's principle. We mentioned this when we discussed the Haber process. Metabolic reactions, as well as industrial processes, make use of this effect to continuously make products in equilibrium reactions. This is production of ethyl acetate. You may have heard of ethyl acetate. It's one of the chemical compounds in non-acetone containing fingernail polish remover. Don't judge. So when you're considering all the possible reactions of industry, it's always in the best interest of that industry to maximize the production of the desired product, right? So this is another example of a system where you remove product and you continue to influence the equilibrium. So here is just some nutsy boltsy practice on equilibrium. In the equilibrium system, A, B making C and D, if you add A or B, what's going to happen? You're going to make C or D, pardon me. If you remove A or B, what's going to happen? Well, your system's going to work to replace that A and B, consume C and D to make more A and B. If you add C or D to the system, you will try to make more B and A to reestablish equilibrium. If you remove C or D, your system will try to replace C and D will replace C and D in an attempt to reestablish equilibrium. So, again, we have a little bit more detailed example with the actual Haber process here. What happens if we add nitrogen? We would produce more ammonia. If we add ammonia, we would reverse the reaction and produce more nitrogen and hydrogen. What if we add hydrogen? We would consume nitrogen in order to make more ammonia. If we remove ammonia, our system will produce more ammonia. Manipulating temperature. Changes in temperature may easily be treated as changes in concentration if you think of heat as a product in an exothermic process or a reactant in an endothermic process. Okay, so let me write that up here just to be clear about what I mean. If we have A plus B makes C, and we know it's an exothermic process, let's go ahead and give it arrows. If it's an exothermic process, heat must be released, right? So if heat needs to be released and you increase the temperature of the system, what are you in essence doing? What are you doing, right? If you increase temperature of the system, then what is the system going to do? If it needs to release heat, then it's less able to produce heat, and it's going to be driven left. If you decrease temperature in a system that needs heat, it's going to increase production of products to produce more heat. So this is what this question or what this statement says. It's basically viewing your influence on the temperature of the system on either an exothermic or endothermic process. So I'm ignoring K right now because K will change if you increase temperature. But it's showing you with an illustrative process why K changes. An increase in temperature of an exothermic reaction will cause equilibrium shift to the left. K will decrease. Okay? Star that. A decrease in temperature of an exothermic reaction will cause equilibrium to shift to the right, and K will increase. So this example is for exothermic processes, right? So let's put exo, we've been writing in red. So if you decrease temperature in an exothermic reaction, A plus B makes C plus heat. Again, it's exothermic. Heat is a product. If you decrease temperature, the system will work to replace the heat. If you increase temperature, the system will work to replace reactants and remove heat. Let's look at the opposite, the endothermic system. In an endothermic system, we're going to go blue because it's cold. You have A plus B plus energy. I'm going to put heat. This is an oversimplification. This is not thermodynamics, okay? Makes C, or increase in temperature of an endothermic system reaction will cause, or endothermic reaction will cause the equilibrium to shift to the right. If we increase temperature, when heat is a reactant, it's needed, then it's going to use that heat to make products. Okay? K increases when you increase temperature in an endothermic system. A decrease in temperature of an endothermic system makes it colder, will cause equilibrium to shift to the left to produce more heat. K will decrease. This is a logic scenario you have to get your head around, because these are often the type of question that's embedded well within a larger question, where you have a thermodynamic system, you aren't thinking much about equilibrium, and the next question says what's going to happen to the K value if you do this. You have to keep a logical control over the system itself if you manipulate temperature. What's going to happen to my K value if? So here's a couple of examples. I have I have a process that's nitrogen and oxygen making nitrogen monoxide. We have delta H is positive 181 kilojoules. This is an endothermic process because energy is required for it to proceed. If we add heat, when energy is required, we would expect to make products. So it would be product favored. And K will do what? K, well, because we made more products, K will increase. If we lower temperature, opposite's going to happen. Reactant favored, and K will decrease. So we have an example of 2 moles of sulfur dioxide and oxygen making sulfur trioxide, and we have a delta H that's negative. Okay, it's the opposite. It's exothermic. So let's go back to our red pen. Oops, I got to pick an ink color. If I increase temperature in an exothermic process where heat needs to be released, then my system is going to try to consume heat and going to be reactant favored. Reactant favored, and we would expect our K value to go down. If we remove heat, take heat out of the system, our system's going to work to produce it, and so we'll be product favored. This handwriting is amazing, isn't it? And our K value will increase because we're going to produce more products. So hopefully that helps you get your head around all those things. Changes in pressure only affect equilibrium systems having gaseous products or reactants. Increasing pressure of a gaseous system will cause equilibrium to shift to the side with fewer gas particles. So this goes back to us looking at the number of moles of gas on the reactant and product side, only gases, to determine what's going to happen to equilibrium when we change pressure. Decreasing pressure of a gas system will cause equilibrium to shift to the side with more gas particles. Okay, so you kind of want to imagine in your head, you have a gas bulb system, you have reactants, you have products. These have to be of different size for pressure to matter. In other words, you have to have a difference in the number of moles of gas on the reactant and product sides in order to see a change with pressure. If the system has the same number of moles of gas on each side, change in pressure do not affect equilibrium. Stands to reason. Adding an inert gas does not affect equilibrium because partial pressures of gases in the reaction are not affected. Because we know our Kp expression is partial pressure of gases, we know that those partial pressures won't change, okay? Now, granted, the overall quantity of space they take up is different, but it will not change the product of this. So, changing pressure does not affect the value of the equilibrium constant. Very important. So here we go. We have phosphorus and chlorine making phosphorus trichloride liquid. Note the liquid. We have only a gas. So on the reactant side, we have 6 moles of gas. Product side, we have none. If we increase container volume, that's going to lower pressure. That would be reactant favored. That's because we have more reactants. We made the space bigger. Decrease container volume, increase pressure. We're going to go, I need to say reactant favored, not right or left. Reactant favored. And this decreasing container volume will be product favored because we have shrunken the space the gas can take up. If we add argon gas, what's going to happen to the system? Well, gases take up space, right? So because they take up space, what does that say? Well, hold on. Let's go back to our K. Kp is equal to 1 over the partial pressure of chlorine. Well, because the inert gas you added is not part of the system, your overall system volume changes and your partial pressure changes. So the ratio is the same. This isn't going to change. Your partial pressure would remain unchanged. So your K is the same. I'm going to put nothing about it, just a couple dashes. Let's see. We have 2 moles of gas on the reactant side, 1 on the product side. If we decrease container volume, we're going to be product favored because there's fewer moles of gas. If we add helium gas, what's going to happen to our equilibrium system? Well, since all the gases are present in the same equilibrium, nothing. Example, we have 2 moles of reactant gas and 4 moles of product gas. If we increase container volume, what's going to happen? No, I'm sorry, we have 4 and 4. 4 and 4, nothing's going to happen if we increase container volume. Our partial pressures will remain the same because gas moles are the same. And that concludes this video on Le Chatelier's principle.